Hello guys, welcome to another session. So we are going now directly to look at types of interactions. That means types of collision. But then before we look at that, I would still like to explain this, even though it was already done in the previous lesson. But I have to do it as a way of recall so that you get the point clearly and understand detailing. All right, so the original path, if you have not yet exhausted the previous lesson, lesson 1 of dynamics, please rush there now before coming to this one, because this is just the continuation of the first lesson. Thank you. So now U is moving with initial path like this. So now this is theta and this is phi. So you simply have to resolve this and this to their horizontal component. That is why you are having VA cos theta, and then you are also having VB cos phi. So I hope you don't have any issue with that. You can comment. If you have problem with resolution of vectors, you can comment. I will still do it again and explain better. So now, since we're talking about conservation of momentum, what we can say is momentum before and after collision is what? Equal, are the same. So we now equate. So I'm not going to be solving, I will just be explaining from here. We now equate. Now you see the momenta perpendicular to you. You have the momentum before collision 0, and then we have momentum after collision. This is it. So you see that we have resolved the ones that are parallel, the momenta parallel to you and the momenta perpendicular to you. All right, so that's good. Now that's it and done. With free mind of understanding, we can now proceed. If you look here, you can see an equation with solution already, so I will not have to solve it since the solution is already there and I've taken time to explain over there. So we just have to go directly to type of interaction, which is the reason for this second lesson, dynamic part 2. So we're going to look at type of impact, type of interaction, type of collision. When two bodies, they come together, they collide. What are the various types? So the first type I'll talk about is the elastic interaction, otherwise known as the elastic collision. In an elastic interaction, not only is momentum conserved, but kinetic energy is also conserved. So what is an elastic collision? An elastic collision is one in which both momentum and kinetic energy, they are conserved. All right, good. So now, on the macroscopic scale, this is very rare to come by. So it is difficult to have an elastic collision. However, many interaction may be approximately elastic. They may be approximate to being perfectly elastic, and the mathematics of an elastic interaction can be used to model this approximately elastic interaction. So I will not want you to be talking about approximately elastic interaction. Just know that elastic interactions are very rare to come by, and these are interactions in which both momentum and kinetic energy are conserved. Very good. After understanding this that I have said, I would like to say that I would like to take an example of an elastic collision. Let's take collision between two charged particles, such as a proton. No, two protons. Let's take example, the collision of two charged particles, like two protons. This is a collision that we can consider as elastic collisions. However, it is important for us to know that any elastic collision, in any elastic collision, the relative speed of approach before the interaction is equal to the relative speed of separation after the interaction. So, meaning that the speed of approach, when we talk of speed of approach, we mean the speed at which the particle is coming, or the particles are coming, because we're talking about interaction, two particles or more, they come together. So the speed of approach is the coming speed, and the speed of separation is the speed afterward, after impact. So now we are saying that for elastic collision, the relative speed of approach is equal to the relative speed of separation after collision. So that is so good to note. All right. So a good example is the nearly elastic interaction of a golf ball. A golf ball being struck by the much more massive club. Okay. So look down here on your screen. You will see an illustration of what we want to consider elastic collision. All right, so this is a golf club approaching the ball at a velocity of v. This is the velocity. Over here, the club continues to move at a velocity very close to v. After this is already after impact, the ball moves up at a speed of 2v. The speed of separation of the ball from the club is equal to the speed of approach of the club to the ball. In this situation, we can consider an elastic collision. I believe there's nothing I have not explained. Now, guys, we will now delve into the second type of collision, which we'll call it the inelastic interaction, or otherwise known as the inelastic collision. Now, in an inelastic collision, some of the initial kinetic energy is being converted into other forms of energy. For example, internal energy and sound also. Good. So what we are saying that is that in inelastic collision, we don't have conservation of momentum and kinetic energy. So Ke is not conserved. All right. So why will Ke not be conserved? Because in an inelastic collision, some of the kinetic energy will be converted into internal energy, into sound energy, and so on and so forth. So after collision, the kinetic energy will be less than the kinetic energy before collision. Now, as in all, momentum is conserved. So in inelastic collision, momentum is conserved, but kinetic energy is not conserved. That's a point to note. Now I want you to know that there are many numerous Examples. There are, when I say numerous, too many examples, of course. There are many examples of inelastic collision, and as a result, we can also classify it into degrees. The degree to which the collision is inelastic. So as a result, now we can classify as perfectly inelastic. We can classify the first one as perfectly inelastic. We can even talk of partially inelastic, and so on. So for perfectly inelastic, we can talk of a ball striking another ball. Anyway, I'm going to take more examples and explain. We'll get there at the level of the example. All right. Okay, good. So all right. So I'm trying to run some technical issues. Just give me a while so that I'll come back. My power is low. The battery is down, as you can see there. It is almost exhausted. So you just have to. All right, guys. So we proceed from there where we ended. All right. So I was okay. So that's good. We're talking about inelastic collision. We're talking about inelastic collision. So to better understand everything there, I'll have to take an example. We solve it together. So that you understand things well. All right, guys. Take this example. I'll read the question. Then we're going to look at it. A glider of mass 0.20 kilogram is moving at 3.6 meters per second on an air track towards a second glider of mass 0.25 kilogram, which is moving 2.0 meters per second in the opposite direction. So when you do this, you have now to draw and then illustrate this, what they have said. When the two gliders collide, they stick together. So after collision, when they stick together, it is a perfectly inelastic collision. Calculate their joint velocity after collision. So since they stick together, momentum before collision, remember, momentum is always conserved. Good. So but now in this kind of collision, since it is inelastic, kinetic energy is not conserved. All right. So now we are going to use momentum. That's it. This momentum before collision calculated here. Good. Momentum after collision, this and that. Momentum after collision. So we have this. Okay. So after collision, this is their joint speed v. This is the speed that they will stick together and move with. Then the next question say, show that the collision is inelastic. How do you now show that the collision is inelastic? That's where it is important for you to pay attention. You have to show that Ke initial is not equal to Ke final. So the initial kinetic energy and the final kinetic energy, they have to be different. More specifically, the final need to be less. So by the time you do that, you can now conclude that since kinetic energy is not conserved, kinetic energy after collision is less. It therefore means that in this scenario we have an inelastic collision. Alright, so now we're going ahead to the test yourself section. Good. So I'll present a question as usual, and then I'll warrant you to copy them, copy the questions, and then you can go ahead, pause the video, copy the questions, answer them, and then you submit either in the comment section or in the forum. If you have any question, drop it in the comment section for review. Thank you for joining us. We shall see again in our subsequent lesson. This is Godwill Yakum. Bye.